Back by popular demand, I'm going to do a few videos here of some example problems from 7.1 on numerical integration. So as we saw in class, I didn't do a lot in terms of, actually I didn't do anything as far as actually calculating those by hand. We were looking more at error. And so I'm going to do those sorts of problems, three of those, one for the midpoint, one for the trapezoid rule, and then one for Simpson's rule. These are actually all taken from the text. So the first one is actually, it's number 32 from the text, and it asks, so for this integral, we're looking for the area under the curve from 1 to 4 natural log of x. First, it asks us for mn. We want to know, well, let's see, is this right? No. Sorry, in this case, it's M10, right? So specifically for M10, it wants to know if it's going to be an underestimate or an overestimate, all right? So let's just real quick graph this. So there's 1, and then we'll just call that 4. Now, if you recall, natural log goes through this point, so it comes down this way. And then it kind of comes up, levels off, increases without bound, but it increases at a slower rate as x gets larger. So this is what it looks like. So there's a couple ways to determine whether or not the midpoint rule is an over and underestimate. One, you can see that this is, it's basically concave down, even though it's only kind of the left side of it. It is concave down, and if you recall, we said in class that the midpoint rule would be an overestimate if our function was concave down. Also, you can verify that using GeoGebra. So those are the two ways that I would anticipate on the homework. You could just say that it was concave down and therefore it's an overestimate. You could also verify it in GeoGebra. Either way is fine. The other thing that they wanted us to do is to find a bound for the error. All right, so they want us to use our error formula, right? So the error for mn, so I guess technically I should say it's the error for the midpoint rule with n rectangles. An upper bound for it, it's no larger than k2 b minus a cubed over 24 n squared. All right, remember k is the number that is kind of the upper bound for the second derivative of our function, and that is for any x in our interval AB. All right, well, since I've already put that down, let's just go ahead and figure out what number we could use for K2. Well, the first derivative is 1 over x, right? The derivative of natural log is 1 over x, also known as x to the negative 1, which makes it easy to use the power rule to compute the second derivative, which is negative 1 times x, and then we negative 2, which is the same as negative 1 over x squared. All right, now if I take another pen here, negative x squared, negative 1 over x squared, well, that's going to basically kind of come in like this and like this, right? So it's a symmetry around the y-axis. It's flipped. It's like 1 over x squared would be up here, going like this, and it gets flipped over because of the negative. All right. Well, we can see that along our interval from 1 to 4, this is an increasing function, right? So the farthest away it's going to get from the x-axis is going to be right here, right at 1, at the left point, because it's increasing. This is the farthest away it's going to be, because what we want is this absolute value, right? We want the distance from the x-axis that the function gets, the largest it gets. All right, so we can see here then that that's going to happen at 1. So f double prime of 1, that's negative 1 over 1 squared that's -1. But again, we want the absolute value, so that's 1, and we're going to let that be our k2, right? So that's the biggest value in absolute value of our function, or sorry, of our second derivative. So we've got that. B is 4, A is 1, and then N is 10. So the error, the max error for M10 for this particular function on this particular interval. So we're going to use 1 for k2, and then we've got 4 minus 1 cubed over 24, and we're using 10 rectangles squared. That's less than, so what's that? Well, that's going to be 3 cubed times 1, that's 27. 24 times 100 is 2400. And I'm not going to simplify any farther than that. You can use the calculator for that, but this would be our max error. So the two big things out of here, if you wanted to see, this M10 would be an overestimate, and for M10, this would be the biggest that our error would be. So, you know, on the order of 0.01. Okay. Let's look at the next example. So in this case, we are looking at, this is actually number 34 in the text, looking at the integral from 0 to 1 of x to the 4th dx. And they want us to find the value, the number of rectangles, n, so that Tn, a trapezoidal rule with however many rectangles, that the error, so I guess, yeah, I should say error again, right? Error. The error associated with the trapezoidal rule with n rectangles is less than or equal to 10 to the negative 6. All right. Well, remember the error associated with Tn is also less than or equal to k2b minus a cubed over 12n squared. All right, so if we want the error less than 10 to the negative 6, and this is the max error, then what we need to do is set this equal to 10 to the negative 6, and then try to find the value of n. Now remember, generally, you're going to have a given function on a given interval. So that will determine your k2, that will determine your b minus a. The only thing we can really work with here is the n. We want to find n so this whole expression is equal to 10 to the negative 6. All right, so let's start with k2. Remember, well, we just did it, but you know, it's the number that is basically the upper bound for the absolute value of the second derivative. So here's my f. So f prime is going to be 4x cubed. F double prime is 12x squared. All right, and we're on the interval 0 to 1. So graphically, we can think about it. We have basically a parabola. All right. Well, not symmetric, but just pretend. Okay, so 12x, we know it goes through, right? When x is 0, y is 0. But when x equals 1, then y equals 12. Right? Now you can see from 0 to 1, this is an increasing function. All right, so the biggest that this is going to be on this interval is right up here at 12. So if we let k2 equal 12, then we know that f double prime in absolute value will always be less than or equal to 12, right? Because that's the biggest it gets. All right, so we've got our 12. So let's take a look here now, filling in what we know here. So we have 12. B minus a, that's just 1 minus 0 cubed over 12n squared, and we want that to be equal to 10 to the negative 6th. All right, well, the 12s, we can just divide those out. That's just 1, so I have 1 over n squared equals 10 to the negative 6. And I want to solve for n, so let's multiply both sides by n squared. So now I get 1 equals 10 to the negative 6 times n squared. And then I can divide both sides by 10 to the negative 6. So I have 1 over 10 to the negative 6 equals n squared. Actually, this just shows you, actually, if you have something like this, you can just swap them. but this is why you can swap them. And then, this actually is the same as 10 to the 6th. All right. So what we want to find is the number n, so that if I square it, I get 10 to the 6th. Well, one way to think of it is I could raise this to the 1/2 power, which is the same thing as taking the square root, both sides, and if I take a power to a power, I multiply, so this is 10 cubed, and that's n, and that's another way of saying 1,000. So we would need 1,000 rectangles, well, technically trapezoids, right? 1,000 partitions for the endpoints that we would use for our trapezoids, so that so basically T1000 is the answer. That would give us very, very little error for estimating that particular area under that curve along that interval. All right, last one then. We're going to find a bound for the error. This is number 43 in the text. We're going to find a bound for the error. So we want to use S40 to approximate this integral. All right. So we're looking along the interval from 0 to 5 on the x-axis of 1 plus x to the 4th. All right, and we want to see what the bound for the error would be if I used 40 partitions of Simpson's rule. All right, well, we know that Sn, so the error associated with Simpson's rule using n partitions, is less than or equal to k4, 5 minus 0 to the 5th. So these are the endpoints of our interval, and it's going to be 180, and then it's n to the 4th, but in this case n is 40, so we have 40 to the 4th power. So the trick here is to find k4, and actually the way this is stated in the text is it tells you to use a computer algebra system. That's what the CAS stands for, and we could use GeoGebra as a computer algebra system. So basically what I would expect you to do here is to, well, let's remember what K4 is first. K4 is the upper bound, right? It's greater than or equal to the 4th derivative of f. And that's going to be good for any x in our interval from 0 to 5. So what I would expect you to use GeoGebra for is basically to graph the 4th derivative of this function. All right. Now, real quick, just as a reminder, you may or may not know this. I don't know if you've used this in this class, but you can, if you type in derivative in the input bar, and then just fill in f. If you've already defined this to be f, it'll just give you the derivative, and it'll call it f prime, and then you can find the derivative of f prime, and so on. So I'm not going to go through actually doing all those derivatives. For this part, I'm just going to say use GeoGebra. Okay, but I will say that you end up with a function that looks sort of like this, at least between 0 and 5. It starts up here, and then it goes down pretty far, and then it bounces back up pretty quick, and then it kind of levels off. All right. This is actually like 1 right here, so I think we're way out here by the time we get to 5. All right. Now this right here, that's 12, but it goes down to negative 14. So the question is, well, what's going to be my K4? Well, remember, because of the absolute value, we're looking at the maximum distance from the x-axis that the 4th derivative takes. Well, that's going to be, just use another color here. That's going to be this distance right here, right? That's farther away from the x-axis than this. So even though this is negative because we're taking the absolute value, then we would let K4 be 14. So now we have the last piece to our formula. So this is going to be 14 times 5 to the 5th power over 180 times 40 to the 4th. All right, and I actually worked this out to what number it was, and just realized that I actually took 5 squared into the 5 to the 5th. So what I did is not right. But you can do this on your calculator. It's going to be a small number. S40 is going to be a very good approximation for this function on this interval. So I would just suggest go ahead, crunch that in your calculator, and that would give you what the maximum error is. But it's going to be on the order of something like 10 to the -7th or 10 to the -8th. Very, very small error after just 40 partitions for Simpson's rule. All right, well, those are the types of problems that are on the homework for 7.1. And I do encourage you to use GeoGebra, especially when you're finding these k-values, these bounds on what the maximum value of the second or fourth derivative could be on the interval.